In the previous video, we were given this problem where we have f of x and we had to find the critical points using the first and second derivative tests. And they said check your answer by graphing. We haven't done that yet, so we might as well. And then we're going to find the inflection points and intervals where the graph are concave up and concave down. So if I first check by graphing, I'm going to take my calculator and I'm going to plug in f, because that's really what we're concerned with here, is what f is doing. So 3x to the fourth minus 4x cubed plus 6. So our last problem showed that we have a critical point at 0, at 0 and 1. And I said right away that that's going to be weird because of that relationship. And sure enough, the first derivative test and the second derivative test showed that something different was happening there. So basically, that's neither a max or min, and x equals 1 is a local min. So if I graph this guy, I don't know, I'm going to start at a standard window. You can see all kinds of interesting things happening here. So I'm going to zoom in right to that part right there. So I'm going to do zoom box number 1. And you can see as I'm moving my key that I have a little plus sign there. So I'm going to tell the calculator to look just right in this area. So if I hit enter, I can scroll down and it creates a line. I always like to see my axes in reference, so I'm going to go a little bit past the axes and go this direction. And so the calculator is going to zoom right into that spot that the box is surrounded in. Hit enter. So you can see obviously here we have two critical points. We have a decreasing graph, but right there in the middle you have a 0 slope. So x equals 0, so that looks correct, that our critical point is 0. And then here, if I look at my x scale is 1, so that tick mark should be at 1. So x equal 1 is a local minimum. So we check our work, and that's fine. Our work supports our graph. That's important. Now the next part is talking about concavity. So find the inflection points and the intervals where the graph is concave up and concave down. Inflection points in concavity have to do with the second derivative. So I have the second derivative right here. So I'm going to kind of box this off so everything when I scan this in is all on one page, so you don't have to look at different pages. So I'm not actually going to do anything named the second derivative test. I'm just going to use the second derivative to find inflection points and concavity. I know that all happens in between the points. This all happens in between the places where f prime has an inflection point, or where f double prime is equal to 0. So inflection points, that's where f double prime of x equals 0. That's where 36x squared minus 24x equals 0. Factor out the greatest common factor. That's going to be 12x, I believe. So that's left with 3x minus 2. So that means if that product equals 0, 12x could be 0, and 3x minus 2 could be 0. So x is equal to 0 in this case, and 3x equals 2, x equals 2/3. So my inflection points occur at x equals 0 and x equals 2/3. Now I'm putting them on a number line, not because I'm going to be performing any test. It's because that's going to tell me where the graph is concave up and concave down, because the signs of the second derivative tell me what's happening to f's concavity. So just like before, I'm going to select numbers out of each interval and evaluate the second derivative at those values. I think 1/3 is in there. And here I'm going to do 1. Go over to my trusty machine. I'm not going to erase that. I am just going to put the second derivative in here. That's going to be 36x squared minus 24x. Oh, I hear a fly in here. Oh. All right, delete this out. Plug in x equals 0. Oh, I already know what that's supposed to be. Let's plug in my points here. So I'm going to plug in minus 1, 1/3, and 1. Again, pick convenient numbers. So that looks like a positive number, a negative number, and a positive number. So positive, negative, positive, positive, negative, positive. Now again, I'm not classifying anything. I'm just taking my number line and separating the concavity of F. So I would say F has inflection points at x equals 0 and x equal 2/3. F is concave up on the intervals from, okay, so if f double prime is positive, that means F is concave up from -infinity to 0. Also from 2/3 to infinity. And then F is concave down on the interval from 0 to 2/3. So in your brains, you have to separate second derivative tests and inflection points and concavity. I know this looks the same, but it's not. It's telling you completely different information, and try to be very careful about how you assimilate that information and save it in your long-term memory. All right, thanks.